Now, here we have a simple problem. As you can see in the figure, the velocity of water is 8 meters per second and at point 2, and the pressure is 140 kilopascal on the discharge, meaning if the flow is from left to right, the discharge side is in the point 2. So, therefore, the velocity, the 8 meter per second square is a velocity at point 2, since at point 2, that is the discharge side of our pipe, and the pressure is 140 kilopascal in point 2. Now, the velocity at the point 1 and pressure is also given, in which velocity sub 1 is equal to 4 meter per second and the pressure at 1 is equal to 90 kilopascal. So the diameter of the pipe from the left side is 600 millimeter. There is a pipe in between, as you can see in the picture. So requirements to solve this problem is: first, what is the head of the pump if the velocity is 4 meter per second and the pressure is 90 kilopascal on the suction side of the pump? So meaning, if it is in the suction side, flow of water will come from point 1 to point 2. So next, how much power is required to drive it if the diameter of the suction side is 600 millimeter, and as you can see in the figure? And third, if the pump is rated at 120 horsepower, what is the efficiency of the pump, neglecting energy losses in the system? So let's solve this problem.
Okay, so to solve this problem, let us consider the Bernoulli's energy theorem, that the energy at point 1 is equal to the energy at point 2, in which the pump will add energy to the system. Now, the equation will be V squared over 2G at point 1 plus P1 over unit weight of water plus A1 plus EP, or the energy added by the pump, is equal to V2 squared over 2G at point 2 plus P2 over unit weight of water plus Z2. So since the point 1 and point 2 is in the same elevation, so there's no change in the elevation between point 1, the pump, and the point 2, this will be 0. So the rest were given, then therefore solve for E sub P, or the energy by the pump. Okay, so following the Bernoulli's energy equation, therefore our equation will now be equal to 4 meter per second quantity squared over 2 multiplied to the gravity, which is equal to 9.81 meter per second squared, plus the P1 is equal to 90 kilopascal over 9.81 kilonewton per cubic meter, which is the unit weight of water, plus the E sub P, or the energy added by the pump, equal to, at point 2, 8 meter per second quantity squared over 2 multiplied to the gravity, 9.81 meter per second squared, plus 140 kilonewton per meter squared, which is the pressure at point 2, over 9.81 kilonewton per cubic meter, which is the unit weight of the water which is flowing to the pipe. So solving for the head of the pump, which is E sub P, we will get the head of the pump equal to 7.54 meter. Number 2, how much power is required to drive it if the diameter of the suction side is 600 mm? Power P is equal to the discharge Q multiplied to unit weight of water multiplied to the energy. The Q is the discharge. So to compute for the discharge Q, we will use the formula that the discharge Q is equal to the area multiplied to the velocity of the water. The area in which the fluid is flowing is equal to the area of the pipe. The discharge Q is equal to the area multiplied to the velocity. The cross-section of the pipe is a circle. Therefore, to compute for the area, we will use the formula pi over 4 multiplied to d squared. The diameter of the pipe is equal to 0.6 meter. And the velocity is 4 meter per second. The discharge Q will be equal to 1.131 cubic meter per second. Now, we can solve for the power, in which it is equal to the discharge multiplied to the unit weight of water times the energy of the pump. Power, P, it is equal to Q, or the discharge, multiplied to the unit weight of the fluid. In this case, it is a unit weight of water multiplied to the energy. So, to solve for P, our discharge was solved and it was 1.131 cubic meter per second. Unit weight of water is equal to 9.81 kilonewton per cubic meter, and the energy of the pump, or the head of the pump, is equal to 7.54 meters. Now, if we look at the units, the resulting unit will be in kilonewton meter per seconds, or kilowatts. And the answer is, the power is equal to 83.66 kilonewton meter per second, or 83.66 kilowatts. Okay, so now we are done with number 2. Number 3, the question is, if the pump is rated at 120 horsepower, what is the efficiency of the pump, neglecting energy losses in the system? So to compute for the efficiency is equal to the output over the input multiplied to 100% to get an answer in percentage. The input is the power that the pump is at 100% efficiency, and the output is the actual energy the pump is, or actual power that the pump is performing. So the input is equal to 120 horsepower, but the output, which is in 83.66 kilowatts, the units must be the same. So the input is in horsepower, therefore let us convert the output into horsepower as well. So 1 horsepower is equal to 0.46 kilowatts. So the output is equal to 112.144 horsepower. Let's compute for the efficiency. Efficiency is equal to the output, which is 112.144 horsepower, over the input, 120 horsepower, multiplied to the 100%. So therefore, the efficiency is equal to 93.45%. So that is our answer for this example problem.